Assalamualaikum and good day to all of you. We are now into chapter 2, first order differential equations, and in this chapter we are going to learn how to solve first order differential equations. And the differential equations which we are going to focus on are separable equations, homogeneous equations, linear equations, Bernoulli equations, and exact equations. So let us start by discussing separable equations. Let us look at the definition of a separable equation. A first-order differential equation is said to be separable or to have separable variables if dy dx is equals to g of x times h of y, where g of x is a function of x alone and h of y is a function of y alone. Okay, so this is a differential equation of first order because the highest derivative that appear in this equation is 1. And on the right side, we see a product of two functions. One of the function is labeled as g and the other function is labeled as h. The function g, which can be of any function, is expressed solely in terms of x, whereas the function h, which can also be any type of function, is expressed solely in terms of y. So if we see this kind of expression, dy dx equals to a product of the function g in terms of x with the function h in terms of y, so we consider this as a separable differential equation. Procedure for solving separable equations. Given a first-order differential equation, which is in the form of dy dx equals g of x times h of y. Now, we now know that this is a separable equation. dy dx is a product of two functions. One of the function is in terms of x alone and the other function is in terms of y alone. So to start solving this separable equation, we need to separate the variables x and y. So bring the function h in terms of y to the left side. So we get this expression on the left side, dy divided by h of y, and bring the differential dx to the right side so that we get this expression g of x dx. Notice that the variables have been completely separated. The function in terms of y alone is now placed on the left side, and the function expressed in terms of x alone is now on the right side of the equation. Now once this is done, we need to integrate the left side of the equation with respect to y. So perform the integration of 1 over h of y respect to y, and we need to integrate the right side of the equation with respect to x. So perform the integration g of x with respect to x. And after we have performed the integral, we have to add the parameter c. So let's solve some problems. Solve the following first-order differential equations by separation of variables. Express your solution in explicit form if possible. So here's the first question. dy dx equals e power of 2x minus 4y. Is this a separable equation? So to find out, let us firstly apply the law of exponents. Okay, so one of the laws says that e power of a minus b is e power of a times e to the negative b. So we are going to apply this law of exponent so that e power of 2x minus 4y can be rewritten as e to the power of 2x times e to the negative 4y. Okay, apply this law. And notice that the right hand side of this equation matches the general form of the separable equation. On the right side of a separable equation should contain the product of a function in x with a function in y. So in this case, the g of x is e to the power of 2x and the h of y is e to the negative 4y. So for this given differential equation, it seems that it contains a product of an exponential function expressed in terms of x alone with another exponential function expressed in terms of y alone. So let us solve this equation or this separable equation by separating the variables. Bring e to the negative 4y to the left side and bring the differential dx to the right side. So we get dy divided by e to the negative 4y equals e power of 2x dx. We can continue by bringing e to the negative 4y to the numerator so that we get e to the power of 4y dy equals e power of 2x dx. Next step is to integrate the left side of the equation with respect to y and the right side of the equation with respect to x. So we have to integrate e to the 4y with respect to y and integrate e power of 2x with respect to x. Using the formula of the integration of e to the power of ax dx is equals to e to the power of ax divided by a plus a c. Now a is any constant. Okay, so we get this formula actually by applying the substitution technique of integration where we let u equals to ax. So applying this formula of integration for the integral of e to the power of 4y with respect to y, we get the answer as follows: e to the power of 4y divided by 4, where in this case a is 4. Okay, a is 4, so you have to divide by the constant 4. And integration of e to the power of 2x with respect to x, you get e to the power of 2x divided by 2. For this case here, a is equal to 2. Okay, equal to 2 divided by 2. So e to the power of 2x divided by 2. Now on the left side, after we have performed the integral, we have to add the constant, which we are going to label as the c1. And on the right side, after performing the integral, we write down the constant, which we label as the c2. Now let us combine these two constants. Bring c1 to the right side, you get c2 minus c1. But c2 minus c1, a constant minus another constant, will result in a new constant, which we shall label it as a c3. Okay, for example, 4 minus 1 is 3. So 4 is a constant, minus 1 is a constant, will result in a new constant. Okay, so c2 minus c1 is equal to c3. So we have actually solved the separable equation, but this solution of the separable equation is in implicit form. So we consider this as an implicit solution for the given separable equation. Can we transform this implicit solution to explicit solution? Yes, we can. What you have to do is to firstly multiply the whole equation by the number 4 as follows. And then we apply the ln on each side of the equation. But before that, notice that 4 times c3, 4 is a constant, times another constant will result in a new constant. So we call it as a c4. And then we apply ln on both sides of the equation. Ln e to the power of 4y equals to ln 2e to the 2x plus c4. Now we can apply the law, another law. Ln e to the power of a is equals to a, and therefore ln e to the power of 4y is 4y. So 4y is equals to ln of 2e to the 2x plus a c4. In other words, y is equals to a quarter ln 2e to the 2x plus a c4. And this solution is now in explicit form because the solution is expressed in the form of y equals to a function in x. Y is expressed explicitly in terms of x, and therefore we consider this as an explicit solution for the given separable equation. Now take note that in this example of the solution, I label the C's as C1, C2, C3, and C4. Now, from now on, we are not going to label the constants. Instead, for every constant, we're just going to call it as a C. For example, C2 minus C1, I'm just going to call it as a C. Okay, that means this C3 will be known as a C. And okay, so this C3 also call it as a C. C4 is also as a C. Okay, so every constants, we don't have to label them anymore. We just call the constants as a general C. The second problem is to solve xy cubed dx plus ye to the negative x dy equals to 0. Is this equation separable? It seems that this equation is not expressed in the standard form of a separable equation, which is dy dx equals g of x times h of y. Instead, this equation is written in differential form m of xy dx, m of xy dx plus n of xy dy, n of xy dy equals to 0. So how do we know whether this equation is separable or not? To find out, the first step is to shift one of these two terms to the right side of the equation. It is advisable to retain the term with the differential dy on the left side of the equation and shift the term with the differential dx to the right side of the equation. This is because at the end we want to express y explicitly in terms of x if it is possible to do so. So we do the following: y e to the negative x dy equals to negative x y cubed dx. Next step is to shift the variables, retain y dy on the left side of the equation and bring y cubed to the left, and retain negative x dx on the right side of the equation and bring e to the negative x to the right. So we get y divided by y cubed dy equals to negative x divided by e to the power of negative x dx. So it seems that we have been able to separate the variables where the function with the variable y is placed on the left side of the equation and the function with the variable x is placed on the right side of the equation. The variables have been completely separated, and therefore we are sure that the equation that we are dealing with is a separable equation. Suppose we find out that it is impossible to separate the variables, therefore we conclude that the given equation is not a separable equation. So this is a separable equation. We are going to proceed by integrating the left side with respect to y and integrating the right side with respect to x. At the same time, we know that y over y cubed is the same as y to the power of negative 2, and negative x e to the negative x can be rewritten as x e to the power of x. What is the integration of y to the power of negative 2 with respect to y? Okay, there are two formulas that we can refer to. Integration of 1 over x dx equals to ln of absolute x plus c, or integration of x power of n dx is x to the power of n plus 1 divided by n plus 1 plus c, provided that n is not equal to negative 1. So for this particular integral, we get y to the power of negative 2. Okay, this x will be replaced by y, and the power of n is negative 2. Negative 2 is not negative 1. Therefore, we are going to use this formula instead of the one up here. Okay, so the result will be y to the power of negative 2 plus 1 divided by negative 2 plus 1, which gives us negative 1 over y. On the right side of the equation, we have to apply the product rule, the integration by parts formula to evaluate this integral, where we find that u is equals to x and dv is e to the x dx. And in the formula for the integration by parts, we require v and du. To get v, we integrate dv. So integration of e to the x dx is e of x. And to get du, we differentiate u with respect to x. Therefore, du is equals to dx. Okay, so this is the result. We have a negative sign out here. And for this integral, apply the formula u times v. So x times e to the x minus integration of v du, e to the power of x dx. Okay, continue. So negative 1 over y is equal to negative. Okay, there's a negative 1 outside the bracket. X e to the power of x, and integration of e to the power of x is still e to the power of x, so minus e to the power of x plus a constant c. After this, we get the following: 1 over y is x e to the power of x minus e to the power of x plus a c. Okay, cancel the negative 1 on the left side and negative 1 on the right. This is what we obtain. So notice that this is already the solution for the given separable equation. However, this solution is in implicit form. Okay, so we regard this as an implicit solution for the separable equation. To get to the explicit form, we write the reciprocal of 1 over y, which is y, and the reciprocal of the whole expression on the right side is 1 over x to the power of x minus e to the power of x plus a c. So this is a solution which is in explicit form. So this solution is an explicit solution for the given separable equation, okay, where y is expressed explicitly in terms of x. For this third question, let us solve dy dx equals to y plus 4 divided by y times x squared plus 4. And notice that the right side of this equation involves a product of a function in y, which is y plus 4 divided by y, with a function in x, which is 1 over x squared plus 4. Now let us start separating the variables. Shift the function y plus 4 over y to the left side, and the differential dx move it to the right side, so that we get the following: y dy divided by y plus 4 equals to dx divided by x squared plus 4. Now we can write dy at the side of this quotient and dx at the side of this quotient which is like this. So you can write y over y plus 4 dy equals to 1 over x squared plus 4 dx. These two equations are equivalent. Okay. Now we know that after this we have to evaluate the integral on the left side with respect to y and integrate the right side with respect to x. So what is the method of integration for the one on the left? What is the integration of y over y plus 4 with respect to y? There are actually two techniques that we can use. One of them is by substitution method, where we let u equals to y plus 4, and the other method is by division. We use division because the power of y at the numerator is the same as the power of y at the denominator. Whenever these two powers are the same, or when the power of the numerator is larger than the power of the denominator, then we can apply division first before we evaluate the integral. So I'm going to apply division to rewrite this quotient in a different form. So how to use the division? Y divided y plus 4. Okay, y is the same as y plus 0. Now let us think of a number. When we multiply by y, we get y. So certainly the number must be 1. So 1 times y, we get y. At the same time, 1 plus times 4 is 4. So we get 1 times y plus 4 is y plus 4. And we know the basic technique of applying this division. We have to take away this top part here with the one below here. So y minus y is 0. 0 minus 4 is negative 4. So this is the remainder of the division. So we can rewrite this quotient in the form of 1, okay, minus the remainder, which is 4, negative 4, divided by the divisor, which is y plus 4. Okay, so we have 1 minus 4 over y plus 4, and this is an expression which we have rewritten for the given quotient. And after this, we will start evaluating the integral. So on the right side, we have not done anything yet. Okay, just keep it as the same as it is. So what is the integration of 1 with respect to y? So of course, we know the answer is y. But for this right side here, we have to use integration by substitution, where we let u equals to y plus 4. Okay, so we let u equals to y plus 4, and du over dy must be 1, and therefore du equals to dy. Okay, evaluate the integral of 1 with respect to y, as I have mentioned just now, is this y minus. Now we're going to replace this by u, integration of 4 divided by u, and replace dy by du, so we get 4 over u du equals to. Now on the right side, what is the technique of integration to apply? We simply have to use this formula given in the table of formula of integrals. Integration of 1 over x squared plus s squared dx is 1 over a squared plus s squared dx. To evaluate this integral is equals to 1 over a inverse tangent of x over a plus a c. Okay, now let us determine the value of a in this given problem. As notice that x is the variable, and therefore a squared must be 4, so a must be 2. So the answer for this integral will be 1 over 2 inverse tangent of x over 2 plus a c. Okay, so notice that we have already done with this integral. It's very straightforward. You just have to apply this formula given in the table of integrals. Now we still have to complete this integration. Integration of 4 over u du, we can apply the formula of integration of 1 over x dx, which is ln of absolute x plus c. So we have a constant 4. So 4 multiplied by 1 integration of 1 over u. And therefore, integration of 1 over u is ln u, ln of absolute u plus a c. So we write y minus 4 ln of absolute u, and on the right side is the same as before. But we have to resubstitute u, because u is the variable that we have introduced. U is equals to y plus 4, so replace u by y plus 4, so you get y minus 4 ln of absolute y plus 4 equals to half of the inverse tangent of x over 2 plus a c. And this is a solution for the separable equation, and it is an implicit solution. And notice that it is impossible to express this implicit solution into explicit form, because we have two functions involving y, and they are of different types of functions. and therefore we know that it is impossible to express from implicit solution to explicit solution. So we have to be satisfied with this result for the solution of this dE. Number 4, dy dx equals y squared minus 4. Notice that the right side of the equation involves a product of a function in y, which is y squared minus 4, with a function in x, which is 1. Okay, so y squared minus 4 times 1. Now shift y squared minus 4 to the left side and shift dx to the right. We get as follows: dy divided by y squared minus 4 equals to dx. Evaluate the left integral with respect to y. Evaluate the right integral with respect to x. Now what's the approach of evaluating the left integral? Now notice that the left integral involves a quotient in the form of 1 over y squared minus 4, and it is possible to factorize the denominator. So what is the factorization of y squared minus 4? We can apply the formula a squared minus b squared is a minus b times a plus b. Okay, so y squared minus 4 will be y minus 2 times y plus 2. Okay, so we shall rewrite this expression on the left as dy divided by y minus 2 times y plus 2. And on the right side is very straightforward. Integration of 1 with respect to x is simply x plus c. Now how do we evaluate the integral on the left? When the denominator contains a product of linear factors such as this, we are going to evaluate the integral by firstly applying partial fraction. We need to decompose this fraction into a sum of two partial fractions. The denominator contains two factors. One of them is y minus 2 and the other is y plus 2. And so for the first partial fraction, we write a divided by y minus 2. And for the second partial fraction, we write it as in the form of b over y plus 2. Okay, so we want to decompose this partial fraction into a sum of two partial fractions. So the question is, what is a and what is b? So there is actually more than one way to find a and b, but I'm going to illustrate to you this technique known as the cover-up method. To find a, since a is above y minus 2, so we write a is equals to, now copy the expression on the left, which is 1 over y minus 2 times y plus 2. Okay, so to find a, since a is above y minus 2, let us cover y minus 2. Covering y minus 2 meaning that we want this to be 0. Now if y minus 2 is equal to 0, so y has to be equal to 2. Next, substitute this number 2 into the y which is not covered. So a is equals to 1 over 2 plus 2, which is actually 1 over 4. Now we're going to apply the same technique for b. Okay, so b is above y plus 2. So the first step is to write b equals to the same as the left expression, 1 over y minus 2 times y plus 2. Now since b is above y plus 2, let us cover the factor y plus 2. So covering y plus 2 is just implying as if y plus 2 is equal to 0. So if y plus 2 equal to 0, y is equal to negative 2. Substitute negative 2 into the y which is not covered. So b is equal to 1 over negative 2, negative 2. In other words, b is equal to negative a quarter. So these are the results for the unknowns a and b. A is a quarter. Now substitute 1 over 4 into a. And b is negative a quarter. Substitute b as negative 1 over 4. So we get the following expression: 1 over 4 y minus 2 minus 1 over 4 y plus 2. So this is the partial fraction decomposition for this given quotient. Okay, so we get two partial fractions. So let us rewrite this expression by using the partial fraction decomposition before we evaluate the integrals. So we get integration of 1 over 4 y minus 2 minus 1 over 4 y plus 2 dy equals to x plus c. Okay, now we know from substitution method, if we let u equals y minus 2, then integration of 1 over u is ln u. Okay, so integration of 1 over 4 y minus 2 with respect to y gives 1 over 4 ln of absolute y minus 2. The same goes for here. If you let u equals y plus 2, so integration of 1 over u is ln u. So integration of 1 over y plus 2 respect to y gives ln y plus 2. Okay, so in other words, the integration of the left side is the same as a quarter ln of absolute y minus 2 minus a quarter ln of absolute y plus 2 equals to x plus c. It seems that we have already solved this separable equation, but is it in implicit form or is it in explicit form? Okay, certainly this solution is in implicit form, so this is an implicit solution for the given differential equation. Now, can we change from implicit to explicit? Yes, it is possible to change from implicit into explicit because these two functions in terms of y, they are of the same type. Both are of logarithmic functions. So let us now illustrate how to change from implicit solution to explicit solution in the next slide. In this slide, I'm going to illustrate to you how to transform this implicit solution which you have obtained in problem number 4 into explicit solution. A quarter ln of absolute y minus 2 minus a quarter ln of absolute y plus 2 equals to x plus c is the implicit solution for problem number 4. I'm going to start by multiplying the whole equation by the number 4. So we get the following: ln of absolute y minus 2 minus ln of absolute y plus 2 equals to 4x plus 4c. Let us apply law of logarithm to simplify this expression. We know that ln a minus ln b is the same as ln a over b. Therefore, ln of absolute y minus 2 minus ln of absolute y plus 2 is the same as ln of absolute y minus 2 divided by y plus 2 equals to 4x plus, now 4 is a constant, multiplied by a constant gives us a new constant, so we are going to label the new constant as just a c. Okay, so on the right side we get 4x plus a c. The next step is to eliminate the ln, and that can be done by exponentiating both sides of the equation. Okay, we apply e on both sides of the equation. So on the left side we get e to the power of ln of absolute y minus 2 divided by y plus 2, and on the right side these two terms are raised to become the power of e. So on the right side we get e to the power of 4x plus a c. If we apply 1e on the left, there must only be 1e on the right. So do not write e to the power of 4x plus e to the power of c. That is wrong. Okay, so on the right side is simply e to the power of 4x plus a c. Now let us apply another law, which is e to the ln a equals to a, and e to the power of a plus b is e to the power of a times e to the power of b. So for the left side, we're going to apply this law. Okay, e to the ln a, this is the a, is a. So e to the ln of absolute y minus 2 over y plus 2 is absolute y minus 2 over y plus 2. And for this right side, we apply this law. E to the power of 4x plus c is the same as e to the power of 4x times e to the power of c. But we know that e to the power of c is a new c because e is a constant. A constant to the power of another constant gives a new constant, so this will become a new c. So c times e to the power of 4x, it can be rewritten as ce 4x, ce to the power of 4x. Okay? Now let us continue. We want to eliminate this absolute symbol. We know by definition of absolute value, y minus 2 over y plus 2 is the same as plus or minus ce to the power of 4x. Okay, so by doing so, we have already eliminated the symbol of the absolute value. But plus or minus c, it means that c is multiplied by plus 1 or c is multiplied by negative 1. Whether it is multiplied by plus 1 or negative 1, it will still be a constant c. So let us rewrite this whole thing as a new c. Okay, so y minus 2 over y plus 2 is equal to ce to the power of 4x. Next step is to multiply the whole equation by this factor y plus 2. So we get y minus 2 is ce to the power of 4x multiplied by y plus 2. Open up the bracket on the right side. Okay, y times ce to the 4x plus 2 times ce to the power of 4x. Okay, collect the terms with the same function y. So bring this term to the left side and factor the y. So y times 1 gives y minus y ce to the 4x, and bring negative 2 to the right side and factor the number 2, so get 2 times 1, which is the number 2 which we have shifted to the right side, plus 2 times ce to the power 4x, and now we write y is equals to 2 times 1 plus c to the 4x divided by this factor 1 minus ce to the power 4x. And notice that y is expressed explicitly in terms of x, y equals to a function in x, and therefore we consider this as the explicit solution for the given separable equation. 2.1.2 Homogeneous equations transformed to separable equations. So there is another type of first order differential equation which is discussed in this section, and that equation is a homogeneous equation. A homogeneous equation can be solved by transforming it to a separable equation. Before we learn how to solve homogeneous equation, let us firstly understand the meaning of homogeneous function. If a function f of xy possesses the property f of tx ty equals t to the alpha f of xy or some real number alpha, then f is said to be a homogeneous function of degree alpha. Okay, so suppose we are given a function f containing two variables x and y. Now we want to identify whether this function is homogeneous or not by doing the following. Replace x by tx, replace y by ty for the given function, and see the end result. If at the end we get this expression, f of tx ty is equal to t to the alpha, where alpha is a real number, multiplied by the original function f of xy. Therefore, this function f of xy is said to be a homogeneous function of degree alpha. Determine whether the functions are homogeneous. The first function is given by f of xy equals to x squared minus 3xy plus y squared. Now how do we test whether this function is homogeneous or not? We test it by replacing x by tx and replace y by ty. Okay, so this is the original function. So for every x, we have to replace it by tx, and for every y, replace it by ty. So f of xy is x squared minus 3xy plus y squared. Therefore, f of tx ty is equals to tx everything squared. Okay, replace x by tx minus 3 times tx. Okay, this tx is replacing the x in this term, and multiplied by ty, this ty is replacing the y in this term. Plus, now originally it is y squared, now it will be ty everything squared. Now we know that the square of tx is the same as t squared x squared minus 3 times, now t times t is t squared, x times y is xy, plus, now the square of ty is t squared y squared. Notice that for all these three terms, t squared is a common factor, so factor t squared. So in this bracket, we are left with this expression x squared minus 3xy plus y squared. Now this expression inside the bracket is actually the same as the original function. So we say f of tx ty is equal to t squared multiplied by the original function f of xy. Now since we are able to show that f of tx ty is equal to t to the alpha, where alpha in this case is equal to 2, multiplied by f of xy, so we conclude that this given function is a homogeneous function of degree 2. This number 2 refers to the value of this alpha. Another example, f of xy is equal to x power of 5 minus y cubed. Is this function homogeneous? We are going to replace x by tx, replace y by ty. So x to the power of 5 will be changed into tx everything to the power of 5 minus y cubed becomes ty everything cubed. Okay, now tx power of 5 will become t to the power of 5, x power of 5 minus, and then for this term it becomes t cubed y cubed. Okay, now t cubed is a common factor between these two terms. Factor the t cubed, and for the first term inside this bracket we get t squared x squared. Okay, because t cubed times t squared gives t to the power of 5 minus, now after we have factored t cubed, the term inside here will be just y cubed, and notice that the function inside this bracket is not the same as the original function, So we could say that this is not equal to t cubed times the original function. So it seems that f of tx ty is not equal to t to the alpha times the original function f of xy, and therefore we say this given function is a non-homogeneous function. A quick way of determining whether a function is homogeneous or not is by just inspecting the total degree of each term in the function. Okay, now if the total degree of each term in the function is all equals to alpha, then we conclude that the function is homogeneous of degree alpha. Okay, so this is a quick method to determine whether a function is homogeneous or not. We don't have to replace x by tx, y by ty. Let us look at the previous example. Given f of xy equals to x squared minus 3xy plus y squared. By inspection, we can easily recognize that this function is a homogeneous function of degree 2. Why is that so? The first term has a degree 2. The total degree for the second term is also 2, because the degree of x is 1, the degree of y is also 1. The total degree will be 1 plus 1, which is 2. And the degree for the third term is also 2. So each of these terms has a total degree of 2. 2, 2, 2, and therefore we say this given function is a homogeneous function of degree 2. In the next example, f of xy equals x power of 5 minus y cubed. Now it is obvious that this function is not homogeneous because the total degree or the degree of each of these terms is not the same. The first term has degree 5, the second term has degree 3, 5 is not equal to 3, and therefore we say f of xy is a non-homogeneous function. We have already learned the meaning of homogeneous function, so what is a homogeneous equation? By definition, a first-order differential equation in the form of m of xy dx plus n of xy dy equals to 0 is said to be homogeneous if both m of xy and n of xy are homogeneous functions of the same degree. Okay, so if we find out that m is a homogeneous function and n is also a homogeneous function and both of them have the same degree, therefore we conclude that this given first order differential equation is a homogeneous equation. We can easily recognize whether a differential equation m of xy dx plus n of xy dy equals to 0 is homogeneous or not by simply inspecting the total degree or the total power of each term. Example, by inspection determine if the following differential equations are homogeneous. Okay, look at this equation. Is this a homogeneous equation? This is the function m. Now m has two terms. The first term has degree 1 and the second term also has degree 1. Now these two terms are of the same degree and therefore we say the function m is a homogeneous function of degree 1. For the function n, the first term is of degree 1, the second term is also of degree 1, so we say n is a homogeneous function of degree 1. Since both m and n are homogeneous functions and they both have the same degree, and therefore we say that this equation is a homogeneous equation. Part B, the function m has two terms. The first term is of degree 2, the second term also has degree 2. Because the degree of x is 1, the degree of y is also 1, so the total degree for this second term is 2. Therefore, we say that this m is a homogeneous function of degree 2. For the function n, it contains only one term and this term is of degree 2 and therefore we say n is a homogeneous function of degree 2. Now, since both m and n are homogeneous functions and they are of the same degree, and therefore we say that this equation is a homogeneous equation. Part C, the first term for the function m has degree 1, the second term also has degree 1, but the third term has degree 0. Okay, so it seems that the total degree of each term is not the same, and therefore we say m is not a homogeneous function. For the function n, the total degree is 1 because the degree for the first term is 1, the degree for the second term is also 1, so n is a homogeneous function. Now, because of the fact that M is not a homogeneous function, so automatically this equation is not a homogeneous equation. In part D, the function M is of degree 2 for the first term, and the second term is also of degree 2, and therefore we say M is a homogeneous function of degree 2. For the function N is a homogeneous function of degree 1 because the first term has degree 1, the second term also has degree 1. So N is a homogeneous function of degree 1. Even though these two are homogeneous functions, but M is of degree 2, the degree is not the same as the degree for the function N, which is 1. So since these two do not have the same degrees, and therefore we say that this equation is a non-homogeneous equation. Procedure for solving homogeneous equations. Given a first-order homogeneous differential equation in the form of m of xy dx plus n of xy dy equal to 0, okay, so we want to solve this equation, we choose an appropriate substitution. If m is simpler than n, then we use the substitution x equals to vy. In other words, we want to eliminate x in this given equation by replacing x with vy. At the same time, we also want to eliminate the differential dx and substitute it by v dy plus y dv. If n is simpler than m, use the substitution y equals to ux. And that means you want to eliminate y in the given equation. Y should be replaced by ux, and at the same time, you want to eliminate dy in the equation by replacing dy by u dx plus x du. Okay, so substitute the selected substitution into the homogeneous equation, and we shall see that the equation from homogeneous has been transformed to a separable equation. And we have already learned how to solve a separable equation. So solve the resultant separable equation, and finally we have to resubstitute u or v in the final solution. Okay, so this is the basic step. We shall look at some examples of how to solve a homogeneous differential equation. Solve the given differential equation by using an appropriate substitution. Example number 1, x dx plus y minus 2x dy equal to 0. Now this equation is given in the differential form m of xy dx plus n of xy dy equals to 0. Okay, now from our observation, we easily know that this is a homogeneous equation of degree 1 because both m and n are homogeneous functions of the same degree, which is 1. Now how do we solve this differential equation, or how do we solve this homogeneous differential equation? We are going to compare between m and n, and from our observation, it seems that m is simpler than n. Okay, and therefore we use the substitution x equals to vy and dx equals to v dy plus y dv. So for every x that appears in this equation, we need to substitute it by vy and substitute dx by v dy plus y dv. Okay, so x is vy multiplied by dx, which is given by v dy plus y dv. Okay, so make sure we put these two terms in this bracket because vy need to be multiplied by each of the term in this bracket. Plus y minus 2 times x is vy, dy equal to 0. Okay, now by doing the substitution, we have completely eliminated the variable x as well as the dx. What exists in this equation are the variables y and v. Open up the bracket, we get v squared y dy plus vy squared dv plus y dy minus 2vy dy equal to 0. It seems that y is a common factor for all of these terms, so divide the whole equation by y to get v squared dy plus vy dv plus dy minus 2v dy equal to 0. The next step is to factor the differential dy, okay, as follows, and inside this bracket we write down the coefficients for the dy: v squared minus 2v plus 1 dy plus vy dy equal to 0, and what we have obtained now is a separable equation. Okay, now from homogeneous equation, it has now been transformed to separable equation because of the substitution that we have performed. Okay, so we solve the separable equation by firstly shifting this term to the right side. So we get v squared minus 2b plus 1 dy equals to negative vy dv. dy over y is equals to negative v dv divided by b squared minus 2b plus 1. Okay, we need to evaluate the integral of the function in terms of y with respect to y and evaluate the integral of the function in terms of v with respect to v. And take note that for the denominator of the function in v squared minus 2b plus 1 can be rewritten as v minus 1 squared. Okay, so to evaluate the integral on the right, we are going to use the substitution method where we let u equals to v minus 1 and hence du is equals to dv and v must be equals to u plus 1. Okay, so integration of 1 over y with respect to y is simply ln of absolute y, and on the right side we'll get negative integration of, now v is equals to u plus 1, so change v as u plus 1 and dv replaced by du and v minus 1 squared. Okay, v minus 1 is equals to u and then you square it. So for this part of the integral, notice that we can apply term-wise division in order to simplify this expression. When we say term-wise division, it means we are going to take the first term divided by the denominator plus the second term divided by the same denominator. Okay, so on the left side we still have the expression ln of absolute y, whereas on the right side is negative integration of u divided by u squared is 1 over u plus 1 over u squared. Evaluate this integral with respect to u. Ln of absolute y is equals to negative integration of 1 over u with respect to u is ln of absolute u, negative positive is negative, and integration of 1 over u squared du is equals to negative u to the power of negative 1. And at the end, we add the parameter c. But we know that u is v minus 1, so resubstitute. We write ln of absolute y is equal to negative ln u absolute of v minus 1 minus minus is plus, u to the power of negative 1 is the same as 1 over u, or in other words it is the same as 1 over v minus 1 plus a c. But we know that x is equal to vy, which means that v is equals to x over y. So resubstitute v as x over y in this step of the solution. So we are getting the following form: ln of absolute y is equals to negative ln absolute value of v, which is x over y, minus 1 plus 1 over v replaced by x over y minus 1 plus a c. Okay, so this is the solution for the given homogeneous equation, which is expressed in implicit form. Second equation, y squared plus yx dx minus x squared dy equals to 0. Now this equation is given in the differential form m of xy dx plus n of xy dy equals to 0. The function m is a homogeneous function of degree 2 and the function n is also a homogeneous function of degree 2. So both m and n are homogeneous functions of the same degree, which is 2, and therefore we consider this equation as a homogeneous equation of degree 2. So how do we solve this homogeneous equation? We compare m with n and it seems that n looks simpler than m. Now since n seems simpler than m, we use the substitution y equals to ux and dy equals to u dx plus x du. So let us perform the substitution. Y squared becomes ux everything squared plus yx becomes uxx dx minus x squared, and the dy is replaced by u dx plus x du equals to 0. Open up the bracket. Ux everything squared dx becomes u squared x squared dx plus uxx dx becomes ux squared dx minus x squared u dx becomes u minus u x squared dx minus x squared x du becomes minus x cubed du equals to 0. Okay, let us now simplify this whole expression and divide everything by x squared. Okay, it seems that we can eliminate these two terms, and after dividing by x squared, we get the following: u x squared dx minus x du equals to 0. Now shift one of these terms to the right side. X du equals to u squared dx, and it is very obvious that this equation is a separable equation where we can easily separate the variables u and x. So notice that originally we are given a homogeneous equation, but after we have performed this substitution, the homogeneous equation has been transformed to a separable equation. Now let us separate the variables. Okay, we get the integration of du over u squared equals to integration of dx over x. And when we integrate 1 over u squared with respect to u, the answer is negative 1 over u. Integration of 1 over x with respect to x is ln of absolute x plus a c. But we know that y is equals to ux, and therefore we need to replace this u by y over x. Because u is the newly introduced variable, whereas the original variables in the equations are y and x. Right, so negative 1 over u is the same as negative 1 over y over x, which is the same as negative x over y, is equals to ln of absolute x plus a c. Okay, now this is the solution for the homogeneous equation, but this solution is in implicit form. Here we are getting an implicit solution for the homogeneous equation. Let us figure out how to transform this to explicit solution, and we can do so by getting the reciprocal of the left side of this equation. So that will be negative y over x, and we do the same for the right side. The reciprocal of the right side of the equation is 1 over ln of absolute x plus a c. And now we can express y explicitly in terms of x. So y is equals to negative, okay, bring x to the other side, negative x divided by ln of absolute x plus c. Okay, so this is the explicit solution for the given homogeneous equation. So this is the end of our lesson in section 2.1, where we have discussed two types of equations. The first equation is the separable equation, and the second equation is the homogeneous equation. To solve the homogeneous equation, we have to use an appropriate substitution that will transform the homogeneous equation into the separable equation. So it is very important that we know the technique of solving the separable equation, so that not only we can solve the separable equation, but at the same time we can also solve the homogeneous equation. Thank you.